What is going on, guys? My name is Amos and I'm back again with another video. So in this video we are going to be talking about le raisonnement par contre-exemple. Now this is going to be the easiest of them all because all you have to do is to just look for that one contre-exemple, or that one number, that one function, that one object that is going to make everything false. Alright, so now the goal of this raisonnement par contreposé is to show that the proposition for every x, maybe let's say in a set, let's say B, let's say for every x in the set B, we have the proposition P of x, for example, the predicate P of x, for example. Now, the goal of this raisonnement par contre-exemple is to show that this is false. So now our goal is to show that this is false. So showing that this is false means showing that its negation is vrai. Alright, so our goal would be to show that this proposition is what? Is false. Or rather, I would say that its negation is true. So we know that this proposition, alright, B P of x, we have that this is going to be il existe x dans B, il existe x dans B. And then we must have here non P of x, or we can have non P, whether it is a proposition or an assertion. So this has been quantified. So this is where we can now think about a reasoning by contre-exemple. So it is to basically show that this quantified proposition is actually false, or showing that its negation is going to be what? Its negation is going to be true. Alright, so now let me give you guys an example. So now this example, I want this example to be as simple as possible. So let's now consider functions. So we'll talk about functions in chapter 2 we'll talk about functions in greater details or in greater depth when we get to chapter 2 and start to talk about relations and functions. So for now, let's say we have functions whose domain of definition is a set of real numbers, and the range or the codomain, we'll talk about the differences. Let's say the range or the codomain is also the set of real numbers. So let's consider those functions. So let's say we have this set. Now let me call this set A. Let's say I have the set A where we have f, the domain is R and the codomain is R, such that f is a function, So, and then let P be the proposition that f is either even or odd. So let P be that proposition. So take any function whose domain of definition is R and the codomain is the set of real numbers again, then that function is either odd or even. So now we are given this as a proposition. Alright, maybe let's say we have this, let the proposition R, okay, let this be the proposition P, that f is either odd or even. So my goal would be to find an example that is going to make this entire thing false. So I'm going to look for something, an object, or maybe in this case I'm going to look for a function that is neither odd nor even, that is going to make this false, or rather it is going to show that the negation of this is actually going to be true. Now I'll tell you guys that the function f of x is equal to e to the power of x is going to be our counter example. So this is going to be our counter example. Now let me now justify that this is our counter example. Well, first of all, let me start by defining what it means for a function to be even. So a function is even. Now we're talking about the real, we are in the set of real numbers. So a function f is going to be even. So f is even if f of x is equal to f of minus x. Now this is going to be true for all values of x in the set of real numbers for simplicity here. So we can have another set here. So f is even if quel que soit f de x est égal à f de moins x, quel que soit x dans R. So we have that. And then now f is odd. F is odd if f of x is going to be equal to minus f of minus x. This is now for all values of x in the set of real numbers. So this is what it means for a function to be even. this definition here, and this is what it means for a function to be odd. So now I've said that the exponential function is neither even nor odd, so it doesn't satisfy any of these two equations that we have here. So well, let's actually prove that. Let's actually prove it. So let's actually prove that the exponential function is neither even nor odd. Now, graphically, what that means is that the even function is going to be symmetrical about the y-axis, and the odd function is going to be symmetrical about the y-axis, about the origin. What I'm trying to say is that the exponential function is neither symmetric, if we look at the y-axis, or it is neither symmetric about the origin. All right. So now let us show that. So let's say f of x is equal to e to the power x. So now what is f of minus x? So f of minus x is e to the power minus x. But now this is going to be 1 over e to the power of x. So clearly we have that f of x is not equal to f of minus x. So because we don't have this, then this is going to imply that, f is not even. F is not even. All right, f is not even. Now we cannot say that f is odd, because odd is not the opposite of even when we are talking about functions. We have functions that are neither even nor odd. Remember this. All right. So now let's also show that it is not an odd function. Well, we basically have to look at f of x. F of x is basically e to the power of x, and then f of minus x is e to the power minus x. And then we have this is going to be e to the power x. Again, we have that f of x is not equal to minus f of minus x. So because we have this, now this is for all values of x, in the set of real numbers. Because we have this, so the conclusion is that f is not odd. So basically, this is my counter example. So the graph of the function e to the power of x is neither symmetrical about the origin, nor is it symmetrical about the y-axis. All right. Thank you guys for watching, and I'll see you in the next video.